Okay, hello everyone. In this video, we are going to look at 3D vector and parametric equations of lines and planes. We're going to look at the vector and parametric equations of a line, then the plane, and then we're actually going to get to something called the planar equation. And we're going to do some examples along the way. So break out that pencil and paper and work along with me. This stuff is fairly difficult and very visual. So if my pictures don't do you justice, and I won't be surprised if you think so, then go check out the textbook, page 869 to 870. The pictures in there are much better than what I am trying to draw, especially not as an artist. So let's go ahead and get started. All right, so the issue at hand is that in the past, think about how we've described a line in the 2D plane, right? What did you need, right? You needed a point and a slope. But the problem in 3 dimensions is there's lots of lines that have that same slope that go through that point. A little experiment that you can do is take a pencil that you're holding, give it a certain tilt, a certain slope, but then where you're holding it, that point that you're holding it, realize that you can rotate this pencil around that point without changing the slope of that line. So there are many lines that go through a specific point that have the same slope. So a point and a slope is not enough to describe a line in 3 dimensions. So how do we describe lines in 3 dimensions? We use vectors, because vectors are going to not only give you a slope, but give you a direction to go in addition to that steepness. So if I have a line, let me go ahead and get rid of this thing. If I have a line that starts at some point and goes in some direction, maybe it's going down, maybe it pierces the YZ plane here, then enters this first octant, then it continues to go down, and then it pierces the XZ plane right here. I like to put X's when it pierces a plane. Then it goes down, and this does have it's not parallel to the XY plane, so eventually it's going to, boom, pierce this plane, and it's going to continue going on forever. Right? If I want to describe this line in 3D space, I'm going to need a point on the line and then a vector, a 3-dimensional vector in the direction of the line. And then we can simply use the 2D vector equation formula for the line that we learned in 2 dimensions. So let's go ahead and do that. All right, so let's say I have the point 1, -2, 3, and the point 3, 3, 1. And I want a line that goes through these 2 points, all right? The geometry of 2 points defining a line is still true. Let's go ahead and call this A and call this B. But I cannot use slope and point. I need vectors. So let's go ahead and plot these things. We got 1, -2, 3. So that point is going to be about right there. That's going to be our point A. And then we got the point B, 3, 3, 1. So that's going to be a 3, 1, 2, 3, 1, 2, 3, and then up just 1. So we're going to go this far. I'm going to use a different color for this one. You know, I'm actually going to make that first point a different color as well. Give me 1 second. And then this one, let's go with green. So 3. Copy that line. 3. And then 1, 1. Cool. So I want a line that goes through these 2 things, right? So what I need to do is I need to get to one of these points. Let me go ahead and call that B. I need to get to one of these 2 points. It's your choice which one you use. I'm going to go ahead and use A. So I need to get to A. That is going to be my position vector. Remember, it's very important that you understand two-dimensional vector lines in order to understand three. It is a difficult idea. So I have now described with the vector p 1 point on the line. Right. The next thing I want to do is I want to use a vector in the direction of A to B, or any direction that is on this line so that I can describe the entire line. So I'm going to get the vector AB that is in the direction of the line. So I need the vector AB to describe a new point on the line. P plus the vector AB describes the point B. So P describes A, and then AB takes me from the point A to the next point B. And this is another point of the line. P is a point and P plus AB. And then what I can then do is add a multiple, whether it be positive or negative, to describe this whole line. P plus AB takes me here. P plus 2AB takes me here. P plus negative AB takes me about right there. So I can add a multiple of AB to start constructing the line. And there you have it. We will finish this problem in 1 second. But the line, let's go ahead and call it X, is equal to P plus ABT. This blue line, you know what, actually I want to change that color to blue so I'm not confusing anyone. This blue line X is constructed by getting to the line and then adding multiples of AB. So X is going to be some arbitrary vector. P is the vector 1, negative 2, 3. And then AB, what vector is that? That's just going to be 3 minus 1, 2. 3 minus negative 2, 5. 1 minus 3, negative 2. And we're going to multiply that by whatever number you want to start plotting points on this line. And we have now described a three-dimensional line in 3D space. This is a difficult thing to do. There you go. There's your vector equation of the line. Right there, and in practice, right here. And using this, we can start to see like kind of what's happening with this line. Like, is it going down? Is it going up? That's all about the direction vector, right? This is going for every 2 units that you go in the x direction, you're going in the y direction 5, and you're going down in the z direction negative 2. This line is going down. Notice that A is a little bit higher up than B. We're going down as x increases and y increases. Right? As x increases 2, y is increasing a lot. So we're going in this direction. Eventually, we're going to pierce the xy plane. We can figure out when we pierce the xy plane. We just need to figure out when this equation here has a z of 0. Right? That's when we are at the xy plane. When is z 0? We need 3 plus negative 2t to be 0. When is z equal to 0? That's when 3 minus 2t is equal to 0. When is that? That's going to be at t equals 3 halves. And then we can figure out the y and the z when we plug in 3 halves. All right, I'm going to stop there, but essentially what I'm trying to make the point is we can inspect this line using the numbers that we have over here. We are going down and over. We are going to eventually cross through the xy plane. We definitely crossed through the xz, this vertical plane, at some point because we went from A to B, and they are in separate octants. And it looks as though we're also going to pierce through the yz plane at some point over here. We'll just need to figure out when x is 0. All right, it looks like x is 0 at negative 0.5. So there you go. We can inspect lines based on the vector equation of the line. Ooh, and I'm terrible, right? There are z values here. There should be a z here. So if you're screaming getting angry and typing in the comment section, there should be a Z there. All right, this idea over here, though, does kind of nicely segue me to my next point, and that is the parametric equation of a line in 3D. And that just comes from that vector equation. So if the vector equation is x, y, z is equal to some position vector p1, p2, p3, plus some direction vector d1, d2, d3 times a constant, then the parametric equation just kind of cascades from this. X is equal to the x coordinate of the position point plus the x coordinate of the direction vector. Y is equal to p2 plus d2t, and z is equal to p3 plus d3t. Right? So this is the parametric equation of a line in 3 dimensions. Right? You have a parameter t, and giving me that number then determines a coordinate x, y, z. And then, as I was saying before, you can utilize these to know exactly when an x, y, or z value is something that you want. For example, I wanted to know when the z value is 0, or when this line is crossing through the xy plane, when it pierces the xy plane. So I just need to set z equal to 0 there. 4, 11 halves, 0 is when we pierce through. 4, 5.5, 0 is when we cross through. All right, now that I've brought up parametric equations of a line, this would be a good time to talk about the parametric equation of a plane. All right, so how can I describe this plane using vectors and parametric equations? Actually, let me go ahead and add the word vector there as well, because in talking about the parametric equations, we will see the a vector equation of the plane as well. But I want to describe this plane in space, right? And one way to do that is to first declare a point on the plane. Let me go ahead and switch up the colors. Declare a point on the plane, point P, and get yourself to the plane. Right? We've now described a point on this plane. Right? The next thing we want to do is find a point on the plane. Right? If you remember in geometry, planes are defined by 3 points. So we have a point, and if I have another point in the plane, I can then describe a line in that plane. All right? I'll call this point A. Right? And if I have another point in the plane, I can describe another line, right? And it turns out that this is sufficient to describe this magenta plane here, right? Because I have a point, and I can describe any point in this direction. I can describe any point in this direction, but I can also add A and B together. Let's say I want to describe this point right here, right? That's P plus 1A plus 1B. Let's say I want to describe this point right here, right? That's going to be P plus half of A plus B. That describes this point. You can pick any point in this plane, and I can get to it by adding a multiple of A and a multiple of B to P, right? If I want this point right here, all right, I'm gonna get to P. I'm going to go in the direction opposite A, so negative A some amount. And then I'm going to add some amount of B, and I can get to that point. And it turns out that any point in this plane can be described, right? This plane, x, y, z, can be described with a position vector, and then adding PA, some multiple of PA. I'm going to go ahead and say T plus PB. some multiple of PB, I'm going to use the letter S. All right, so a position vector plus a two direction vectors describe a plane in 3 dimensions. Right? How does this relate to the parametric equation of a plane? I can decompose this. So I can have x is equal to, this is going to be p1, the x component of the position vector, plus I'm going to call this a1, the x component of the PA direction vector, multiply that by a parameter, and then b1, the x component of the PB direction vector times the parameter s. All right, we have 2 parameters in the plane. Okay, then y is just going to be the y equivalent of this. So the yp, the ya, and the yb. Right, and the z is going to be p3 plus a3t. Made that like a t, not a plus, and then a b3s. So this is the parametric equation of a plane. We are using vectors and parametric equations to describe a flat surface in space. We get to the plane, and we have 2 directions that describe all the points. There is one necessary feature, and that is PA and PB cannot be parallel. Oh, I don't know why I did a lowercase either. That's weird. Cannot be parallel. Right? If PB and PA are parallel, then we can only still describe a line. It's key that this angle right here is non-zero. Right? So if you have 2 vectors and you're curious, just make sure that vector there, just make sure that these 2 vectors are not parallel. They're not multiples of each other, because then we don't get that that second degree of freedom. All right, let me do a quick example here. All right, if I have the points 7, 2, -2, 5, -3, -1, and 2, 0, 4, if I have these 3 points, let's call them A, B, and C. Right? These 3 points describe a plane. How do I describe that plane? Well, I need to get to this plane somehow. Right? And a point on this plane is, let's go ahead and say it's A. So I need to get, so here's like my origin. Right? I need to get to this point A. So that's going to be my position vector. That's just 7, 2, -2. Right? Then I need to be able to go in 2 separate directions and add those 2 directions to each other. So I'm going to need a point B and C. Right? What is the vector AC? That's just C minus A. So we're going to have 2 minus 7, which is -5, 0 minus 2, which is -2, and 4 minus -2, which is 6. And then I need to go in that direction a certain amount. Let me actually backtrack real quick so I don't run out of room here. -2, 6, t. And then I need to go in this direction. And then I need to be able to add AB and AC. So this was AC, by the way. This was just the origin to A. And this last one's going to be AB. And that's going to be B minus A. So 5 minus 7, that's -2. -3 minus 2, which is -5. And -1 minus -2, which is 1. And I'm going to multiply that by a constant. And then I can go ahead and turn this into a parametric set of equations. So let me go ahead and do that as well. I am going to go ahead and move this stuff up real quick so I have a little bit more room. I want to stay on this page. All right, that'll do. And the parametric equation is going to be x is equal to 7 plus, actually I'm going to go ahead and make that a minus 5t, and that's going to be minus 2s. Y is going to be 2 plus, or minus, I keep doing that, -2t minus 5s. And then z is going to be -2 plus 6t plus 1s, or just plus s. And if you give me an s and a t, that will give me an x, y, and a z that is on this plane. Right? This is the parametric equation, and this is the vector equation. We have two vectors taking us in a specific direction, and we have two parameters taking us in two different directions, all on the surface of this plane. All right, so the next thing I want to tackle is the planar equation of a plane. All right, and to do that, we need to think about something that is true always about a plane. And it's a little bit easier to describe this in person. Most of math is. But just to jump to conclusions here, if I have an arbitrary point in the plane, let me go ahead and call this P, let me call this A, right? No matter where I put this point A, if I were to put A over here, or if I were to put A over here, I need to figure out something that is true about all of these vectors. What is true about all of these vectors? And the thing that is true is that no matter where I put the point A, the vector PA will be perpendicular to some vector that we call the normal vector, right? This vector here, n, kind of defines this plane. If you give me a vector in space and then you stick a plane underneath it, right, that plane is going to be unique if this is perpendicular. All right, with that said, the next thing you need to think about is what is true about perpendicular vectors, right? If I take the vector PA and the vector n, what is true about these two vectors? Well, they're perpendicular, which means that their dot product is 0. They are 90 degrees from each other. Their dot product is 0. And this is the planar equation of a plane. I don't know if you guys just heard that, but a bird just flew into my window. I'm also just now realizing after that bird hitting my window caused me to reflect on life, the universe, and everything, and I'm being redundant by saying the planar equation of a plane. So if you were like, that's redundant earlier, you're not wrong. This is the planar equation. Anywho, what this is saying is if you give me a vector that is normal or perpendicular or orthogonal, all of these are synonyms, to the plane in question, I can then describe the plane. Because, theoretically, you have a point on the plane, and you have an arbitrary point in space, so P is going to be something that you know. Let's go ahead and say that's like X naught, Y naught, Z naught. Why not? The vector A, the coordinate A, is going to be some arbitrary thing, something you don't know. All right, but that's any point on the plane. And then the normal vector, we usually say that the normal vector is just A, comma, B, comma, C. And with this information, something that we know, something that we know, something that is on the plane, we can then write the equation of a plane. So PA, that's just going to be X minus X naught, comma, Y minus Y naught, because I said so, and Z minus Z naught, dotted with A, B, C. And that is 0 because the normal vector is perpendicular to this arbitrary vector PA. Right? And then if you just do this out, you're going to get A times X minus X naught plus B times Y minus Y naught. This is just the dot product, multiplying the component, the corresponding components. And then C times Z minus Z naught. That's all equal to 0. And guess what? A is a number that we know. X naught is a number that we know. B and y naught, c and z naught are all numbers that we know. So if I distribute a and x naught, b and y naught, and if I distribute this all out, they're all going to be constants, which can all be absorbed. So I'm going to write this next line, new color, a times x plus b times y plus c times z plus all those numbers I just referenced, ax naught, bay naught, and c z naught. I'm going to write all those numbers as just its own little constant d. And there you have it. That's the planar equation. That is how we describe a plane in 3 dimensions. Ax plus by plus zz plus d is equal to 0, which is great because if you remember how we describe a line in 2D, it was ax plus by plus c is equal to 0. So the plane equation is just, once again, add a z, and then you have now gone from line to plane. 3 dimensions is a lot easier when you really think about it. It's just adding a third dimension to what we already know. You're not learning anything necessarily from scratch. I will say, sometimes you also see this equation as cz is equal to d, but that's just if I took all these negative values and added them to the other side. But both of these are sufficient to describe a plane in 3D. The big idea here is that you know that a perpendicular vector defines a plane. Right? If you have a point and a vector, you can define a plane. For example, if I give you this point and I give you this vector, right, that is going to be perpendicular to a unique plane. Right? So a vector and a point define a plane. I'm going to write that down in big letters. A vector and a point define a plane. All right? In geometry, you said 3 points define a plane, which is still true. But additionally, a vector and a point also define a plane. This vector is perpendicular to the plane. All right, do that one more time. Here's a point. Here's a vector. All right, that is going to define a specific plane. All right, with that said, I'm going to do one example problem and then wrap this video up. So we have the vector 3, 4, negative 2. And it is perpendicular to the plane. Vector 3, 4, negative 2 is perpendicular to plane. Let's go and call this plane, I don't know, capital P. All right. You'll also notice that when people describe planes, that's the ugliest P I've ever written. When people describe planes, they often use like cursive letters. That's not a cursive P. I digress. But you'll notice that when people describe planes, they often use cursive letters. Cursive capital letters. All right, so we have the vector 3, 4, negative 2, and the point on the plane 0, 1, 2. Right, and this describes the plane. So, and the point 0, 1, 2 is on the plane. What is the equation? What is the planar equation? It's actually a pretty straightforward question to answer. So we have the equation a times x minus x naught plus b times y minus y naught plus c times z minus z naught, and all u equals 0. And all you need to do is plug in what you know. A, B, C was that vector, right? The coefficients are the perpendicular vector. This might be a good time to remind you that ax plus by plus c, the line, ax was the perpendicular vector. This vector was a comma b. Right, so over here we have the perpendicular vector. That's just going to be 3, 4, and negative 2. Because that's all going to be equal to 0. We got a y minus and a z minus. And then we have the point 0, 1, 2. And then we just distribute and simplify. So we're going to have 3x plus 4y minus 2z we're going to have 3, we're going to have a -4, we're going to have a +4. So in total, oh no, this isn't a 3, sorry. It's a 0. So in total, we're going to have a +0 equals 0, right? The d value that was referenced in the previous page is 0 here. So the equation of this plane is 3x plus 4y minus 2z is equal to 0. There you have it. And with that said, I'm going to go ahead and close it out here. We looked at the vector and parametric equations of lines. Then we constructed the plane with vectors and parameters. But then we looked at the planar equation, which used normal vectors. And just this general idea that every vector in a plane is perpendicular to that normal vector. And that created an equation using the dot product. And then along the way, we did some examples. So I hope that I made sense and that you can attempt some on your own. In the homework, you will see some problems that aren't exactly like what I did in this video, but that's because I want you to figure some things out on your own. So good luck with those, but do feel free to send me emails and questions to get some help, because I'm more than happy to help you along the way. But I wanted to give you guys a chance. All right. With that said, I am out.